For the audiences, if you have questions, please do not hesitate. You can just put the question in the chat, then we can assign you later on. Thank you.
Okay, thank you very much. I hope you can see my slides. Again, I'd like to echo the words and thank you very much to Professor Thamasak and Dr. Nakamura for your generous invitation to this conference, and I'm really looking forward to the conversations today. And I'm going to follow on talking specifically about some of the challenges in managing coral bleaching. And we all know that coral bleaching is a rising threat. There's hardly any reef in the world that hasn't faced coral bleaching to date. And if we look at the projections, it's sobering. These are projections for the Great Barrier Reef following the latest CMIP6 modeling. And so what I'm showing you here is the level of intensity of stress or warming that is projected to occur on reefs. And this uses the conventional metric of degree heating weeks. Now, a degree heating week of 8 is what we know tends to give very high levels of stress and starts to cause quite considerable mortality of corals. Now, if we look at that level and we look at the most optimistic pathway for humanity that is projected, this is a sort of sustainability-based economy, or 1.5 degrees of warming, as was just advocated for, you can see that there will be a rise in the intensity of stress, but it should stabilize and end up somewhere like it is today by the end of the century. If we move to 2 degrees of warming, then we see a marked increase in that level of stress, which fluctuates below and above DHW of 8. Both of those futures are going to be stressful. But then if we look at some of the more carbon-rich pathways for future development, we then start seeing very high levels of stress, 3 to 4 times greater than has ever been observed. And it's really hard to imagine how corals would be able to sustain themselves through that. And that's a slightly different perspective than what we normally look at when we consider the frequency of bleaching. So this is the same information, but now we're looking at the number of bleaching events per decade. So again, under the more pessimistic carbon-rich futures, we will see bleaching becoming an annual event pretty much by the middle of the century. But even with the most optimistic climate change emission scenarios, we would still expect to see bleaching events happening maybe every 3 years, every 4 years on average. So they're here to stay. And when it comes to managing coral bleaching, there are sort of 2 research challenges that I'm certainly thinking about, and I know a lot of other people are at this point. The first is to start asking questions about how does the system repair itself? How does the whole ecosystem repair itself? Because it's at that scale that bleaching is having its impact. And then secondly, if genetic adaptation is going to be key to helping corals sustain themselves, even through the most ambitious of our futures, how do we facilitate this? What can we do to facilitate that process? So the first of these questions is sort of moving up a scale in resilience to consider the system as a whole, or systemic resilience. And so this complements what we often do with individual reef scales, looking at resilience, but now asks, how is the whole system connected? How does it repair itself? And if we just look at the Great Barrier Reef, you know, of course, in 1998, it was impacted by bleaching, as was most of the world. 2002, we had another event, and then we had 14 years of quiet, at least from a bleaching perspective. And then we had 3 events in 5 years, which has really been a wake-up call in thinking, how do we deal with this? And is this the new norm already? And of course, the way that reefs must prepare themselves, especially if they've been very severely damaged by coral bleaching, so that there are relatively few corals left on a reef, is those new corals have to come from somewhere. And in many cases, they're going to be coming from reefs elsewhere. So understanding coral spawning and connectivity of larvae is going to be important in helping to understand those processes of reef recovery. And so with the last 3 years of bleaching events, we just asked the question, what's the combined effect on the predicted larval supply across the reef? And overall, what we predict is that there's been about a 70% decrease in larval supply across the whole Great Barrier Reef after those 3 events. And that's sort of commensurate with some of the observed data from field studies on coral settlement that people like Terry Hughes and his team have done. But it's very variable in space. So on this panel, what we can see are reefs that generally sort of heat up quite a bit. We'll come to that. But it shows you the magnitude of larval supply loss, and this is often quite high. In other areas of the reef, which tend to be cooler, we tend to find that the loss of larval supply is much lower. And so there's a lot of variability there. And it's this kind of variability that's going to be important for helping us to manage the reef. Now, one of the most important questions we wanted to ask was, every single bleaching event is different, but is there anything that's predictable about it? Are there some areas that are predictably cooler every time we have a bleaching, or some areas that are predictably warmer when we have a bleaching? And so to look at this, I'll just explain how we've done this. So if we just look at the last 3 bleaching events, which are probably becoming to be a signal of global warming rather than simply ENSO, we can ask, if the thermal stress was essentially randomly distributed in space, how many reefs would you expect to experience no bleaching stress in either of those 3 events? And that would be the 0 on the bottom of my x-axis there. We could also ask, well, how many reefs would you expect to get hit by bleaching 1 time out of 3, or 2 times out of 3, or in all 3 events? And you can compare what you observe to what you would predict under a random distribution of thermal stress. And so if you're looking for refugia, these are areas where there is much less bleaching than you would expect. And this is where we look. These are areas where, under a random model, we would expect very few reefs to escape bleaching in any of those years, i.e. they never seem to show bleaching in those 3 events. But what we observe is about 6% of reefs actually having that kind of probability of actually avoiding any kind of stress. If we want to look at the other extreme, which are the warm spots, here we're looking at reefs that get hit every single bleaching event that they bleach. But in this case, these are reefs that bleach more frequently than you would expect by chance. In other words, there's more of a regular pattern there. They're bleaching at a higher rate. So they're more likely to be areas where there's relatively low circulation that heat up predictably from one event to another. And this kind of information is important. That's one thing. So we know that there's real spatial variability that is at least somewhat predictable from one bleaching event to another. The other ingredient that's helpful is to look at the connectivity pathway. And so here we're using models of larval dispersal to identify those reefs that we call key sources. These are reefs that are exceptionally important sources of coral larvae. That means that they will send larvae to many other reefs, that those connections will be consistent in time, and that the reefs that they connect to often connect to many other reefs themselves. And what we see here are the 500 sort of top most connected reefs out of the 4,000 or so on the reef. And you can see that they're widely distributed across the system. Now, if we go back to that previous thought about the refugia, we know that the refugia ultimately represent about 13% of the reef, but they have the potential to connect to 58% of the reef. In other words, that they can send their larvae to many locations across the reef. And this kind of mechanism can help reefs recover after major bleaching events, because those pockets of healthy coral, or healthier coral, should be able to connect to reefs that have been damaged elsewhere. So that's part of the story. We've got these sort of understanding of this resilience of the system. But then we start thinking about how do you facilitate genetic adaptation? And that's a really complex story. And particularly we need to think about how would you prioritize the kinds of connections between different stress environments? And by connections, I mean connections of larval dispersal and the spread of genes. Now, here's some work that we did about 10 years ago now, which was, I guess, quite arm-wavy by today's standards. And we identified, first of all, two types of thermal stress. The first is what we call chronic stress, which is the typical sort of summer temperature. This doesn't cause bleaching, it's just the nature of variable summer temperatures. So there'll be some areas that have low chronic stress that tend to be cool, and there are areas that are generally much warmer, typically closer to the equator. And of course, during bleaching events, there's always some areas that warm up a little bit and some areas that warm up a lot more. Now, what we didn't know then is in any given bleaching event, we always have known that there are some cool areas and some warm areas. Now we know that some of those areas are actually predictable and consistent from one event to another. But what this does is it gave us sort of four contrasting thermal environments. And we worked with coral physiologists like Roberto Iglesias, Preto, to consider how would corals respond in each of those four boxes. And to put it very simply, this would be the kind of relative response of corals in these different thermal environments. Now, of course, you can use satellite imagery, this is for the Bahamas, to map the locations of those thermal environments. And then you can start asking questions about, well, would you prioritize larval connections between different thermal environments? This is where it starts to become more difficult. Fortunately, there's now a new wave of people doing modeling that combines ecology and evolution, so-called Ecoevo models. And that's throwing much clearer science on some of these questions. So what have we learned from that work? Well, if you're not worrying about evolution and you're really just concerned with what helps maintain a population persist, then we find that complex networks and the inclusion sometimes of random connections is a good thing. And the reason for that's quite simple. If you've got large areas that get damaged, there's potential there for areas much further afield to send larvae and replenish those areas. And you're building that kind of resilience and robustness into the network. But if you're thinking about evolution, things become more complicated. Now, generally, of course, those areas that what I'm calling warm areas, now these are areas that, when I say warm, I mean get really warm during bleaching. They're typically going to be where the greatest selective pressure will be. And it's going to be reliant on existing genetic diversity. Connections from cool areas, from warm areas to cool areas are going to be helpful. But there is a caveat with that. So if you have corals moving from warm areas that are genetically adapted for warmer conditions and they arrive in cooler areas, they may do quite well as those areas warm up. But it depends very much on the kind of trade-off that might come between having greater thermal tolerance and maybe sacrificing either growth rate or fecundity or some other biological process. And this is an area that we still don't know a huge amount. There's some very nice work being done by people like Andrew Baker and Lena Bay on these questions of trade-offs. But this is very important to figure out because there could be some real disadvantages of warm adapted corals arriving in cooler locations. But one of the things that's being sort of discovered in these models, and this is work led by Lisa McManus at the University of Hawaii, is that where you've got limited connectivity across thermal environments, that helps sort of adaptation. And essentially it means that if you have warm areas, that's where there's strong selection pressure. And ideally those warm areas are connected to other areas that are similarly warm so that that selection pressure can drive a direction and drive adaptation, rather than having connections coming in from maybe cooler areas, which sort of dilute the adaptive process by having individuals that don't have any of those adaptive traits. So it's a complex story, because one of the challenges there is that those warm areas, yes, they're under high selection pressure, but that's also where we will see the smallest populations as they're taken out by climate change and bleaching events. So at the moment, one of the recommendations is to try to include a portfolio of different thermal environments and connectivities during the design phase of your management, which might be marine protected areas or something else. And part of this is a challenge because, you know, genetic diversity will tend to come along with larger population sizes. So we know we need larger populations of corals, not just for adaptation, but of course for the functioning of those ecosystems. So there's a bit of a tension there. How do you promote larger population size? Now, the work that we're doing in partnership with the Marine Park Authority is focused very much on the present day here. And we're asking the question, which reefs are most important to promote recovery after bleaching? And this is a simple idea. Imagine you have a bunch of reefs and you know something about how connected they are. These two reefs would be identified as the most connected reefs. But ideally, you would know something about the state of all of those reefs, because if you did, you might know, for example, that this reef, which is healthy, is connected to 4 other healthy reefs and 1 unhealthy reef. Whereas this reef, which is still healthy, is connected to only 1 healthy reef and 4 damaged reefs. And so arguably, this reef is the one that's most important right now because it will be sending larvae where they are needed to reefs that have been damaged. So this is a practical way of trying to identify important source reefs, but it does rely on lots of information on the state of reefs. And for most ecosystems, that's beyond the capability of scientists alone. On the Great Barrier Reef, we have 4,000 reefs. So we're partnering with the citizens of the Great Barrier Reef, with citizen science programs. We have a thing called the Great Reef Census, which is in its 2nd year at the moment, which is, you know, working with the tourism industry and fishing industry, and with as many people as possible to get out there and do simple surveys on reefs to tell us, are they in a good state? Are the corals likely to be contributing? Or are they in a fairly damaged early stage of recovery state? And then that kind of information is taken on board by the Marine Park Authority as they plan where to target their crown of thorns starfish control. And they do this in partnership with the tourism industry. And one of the considerations is, are there some reefs that are ecologically very important that we can reduce other sorts of stresses and protect those coral source populations? And the one, of course, is the crown of thorns. So what do we conclude? Bleaching accelerates even under 1.5 degree of warming. So this problem is here to stay. Systemic resilience is an emerging field. Every bleaching event is unique, but some regions are predictably warmer or cooler than others. We can protect key sources of recovery, and that will help build population size. But I think the strategies to help adaptation are still unclear. There are trade-offs to be made between focusing on warm areas versus cool areas. We can promote population size by favoring our focus on cooler areas, but selection will be more important in warmer places. So we still have more work to do. And I think that in the next few years, we will be able to prioritize where we do restoration, where we protect, with much greater clarity in order to help this pathway of facilitating corals cope with the warming that is already started. And I think all of that is going to involve greater citizen science. We can't do all this as a group of scientists alone. And just lastly, I'd like to thank a whole bunch of collaborators for the work that was being presented.
Okay, thank you very much, Professor Mambi. I'd like to see how there's a question from the audience. Can I ask you some short questions? Okay, it was very nice talk, and I it's very informative and comprehensive for me. There's a small gaps between the conservation or management of the reef systems based on the large system as the Great Barrier Reef. It's one big system, but in terms of our country, like Japan has the chain of small islands. It doesn't have a large riverine systems or terrestrial inputs, but it's probably more localized stresses. So when we considering the conservation techniques or rehabilitation techniques, is there kind of common problems that rise between the large systems like Great Barrier Reef and the small island systems like in Okinawa or so?
Thank you for that question. It's an excellent question, and I'm very fortunate to work with partners and friends in Southeast Asia and the Pacific, and of course the problems are quite different in general on the Great Barrier Reef because of the scale and and relatively modest level of exploitation of many of the species there. So I think that we all share a common challenge of dealing with climate change. And I think that's where the work from a place like the Great Barrier Reef can resonate elsewhere, because some of the techniques are commensurate. But of course, there are other problems, the problems of very high levels of exploitation, local pollution. And I think, for me, one of the challenges is in the same way that we might focus on the importance of temperature stratification in terms of whether those areas are high or low risk, we need to extend that consideration to think about the local stresses as well. So there'll be certain sites that strategically could be very important from an adaptation standpoint, but they are very severely stressed by overexploitation or whatever it is, in which case that might help them prioritize where some of those actions are carried out. But I fully agree that the systems are very different and the problems are more complex in many parts of the world.
Thank you very much. That's very good answer. Is there other questions from the audiences? If you have, please use the chat. If not, then